So we finished looking at Laplace transforms. We're going to see some new tools or new types of functions that you may not have seen before that you run across a lot when you're working with Laplace transforms. And then we'll find out how to use them. So at the beginning here, the setup for this, we're looking at how we can take the Laplace transform of a discontinuous function, one that's at least piecewise continuous. That's necessary for the Laplace transform to exist, but it can have jumps and breaks like this. Now, early on, we did ones like this manually by using the integral and doing it in pieces, splitting up the integral into pieces. But we'll find there are more straightforward ways to do it if we can figure out how to handle piecewise defined function like this. So this function needs to be piecewise continuous, but there can be finitely many discontinuities like this, as we've shown here. So this one is 3 from 0 to 2, and then jumps down to 1, and then moves to t, and then t squared over 10. So the graph looks like the one shown here. So there's an example. Now notice that we're not too worried about less than or equal to for any of these. So these, since they're strictly less than, not less than or equal to, we have holes on both sides here. But you'll see a note a little bit later about this, but in short, it doesn't matter much since we're going to be integrating. If you integrate with again, a finite number of discontinuities like this, it turns out that it doesn't affect the value of the integral because the area under any one value is 0, it turns out. So removing that doesn't affect the value of the integral. So we're going to think about how to find the Laplace transform of something like this. To do so, we need to introduce some new ideas, some new types of functions, and they'll be useful in expressing a piecewise defined function like this by splitting it into pieces. So let me show you those. So these new tools, one's called the unit step function, or sometimes called the Heaviside function, named for a mathematician, Oliver Heaviside. And this unit step function is basically like an on-off button where it can apply to another function and turn it off by multiplying it by 0 and turn it on by multiplying by 1. So it's just defined as 0 for everything to the left of the y-axis and then 1 for everything to the right. And again, the note is here that you don't need to worry about less than or equal to or greater than or equal to because ultimately we're going to be integrating, and so that doesn't affect our final answer. So the unit step function kind of turns things on and off. And you can kind of think about back here, there are multiple functions going on here, but on the first interval from 0 to 2, it's like all of them are turned off except for the 3, and then the 3 gets turned off and the 1 gets turned on, then the 1 gets turned off and the t gets turned on, and so on. So it's kind of like flipping a switch on each part of the function. And so we'll use that to express piecewise defined functions in a minute. But that's sort of the most basic piece here, is this unit step function that's defined as kind of an on-off switch. Then we can step it up to a shifted version of that, which rather than being split at t equals 0, can be split at any arbitrary t value. So that would be the unit step function u of t minus a. Instead of just u of t, if we shift it to the right by a, it would be u of t minus a. If you remember from your pre-calc class, shifting to the right subtracts a value, and shifting to the left adds a value. So it's the same idea, turning on and off, but now it shifts so you can start and stop at any point that you want. And that kind of goes back to that first example. You need to be able to turn the second function on at 2 and turn 3 off there. Then building up from that, you can have a scaled shifted unit step function, which is basically the unit step function multiplied by some value. So instead of being 0 and 1, it can be 0 and 10, for instance, if m is 10. So that's just a extra variation on it. And then the last piece sort of generalizes more It basically turns the step function on and off. So you can have a function being turned on for a specific window and off everywhere else. So this is called the rectangular window function, or the square pulse function, or the boxcar function, a variety of names attached to it. The notation we use is this pi sub AB, and A and B tell you when the thing is turned on, and everywhere else it's turned off. And of course you could multiply this by anything you want to turn a certain function on for a certain window of time. So let's try that example. Let's write down the example that we wrote down at the beginning, this piecewise defined function using this rectangular window function. There is a note here before we do that this pulse function can be written in terms of the unit function, or the unit step, by subtracting the right version. So basically the unit step function t minus a would be turned off here and then turned on from a forever after. Then the unit step function of t minus b would be turned off up until b and then be turned on. And so if you subtract that, starting at b, you start removing all of this, and so it goes back down to 0. So that's why it's the difference in those two unit step functions. So the unit step function is really the foundational piece of this, and then you can shift it by replacing t with t minus a, and then you can switch to a pulse function by defining it in terms of those. So really everything is defined in terms of the unit step function, and it just kind of adds layers to get more general tools that are a little bit more generally applicable. So let's try the example we had, where we had this function and we want to write this in terms of the pulse function. So we're going to write this in terms of step functions. And when I say step functions here, I mean either the unit step function or pulse function, or any other of them. So again, it may help to look at the graph to see how this works, but basically the 3 is turned on from 0 to 2. So that would be 3 times the pulse function from 0 to 2. So the pulse function from 0 to 2 is just equal to 1. And then the next one is then turned on from 2 to 5, and that's 1 times this pulse function. And then that turns off. And then from 5 to 8, you have t. And then from 8 onward, and to deal with this open-ended onward idea, we aren't going to use the pulse function because the pulse function ends at some future time. Instead, we're just going to use the unit function. So t squared over 10 times the unit function at t minus 8. So it starts at 8 and continues indefinitely from there. So if you wanted to, you could then rewrite all of these pulse functions in terms of the difference in step functions, but that's not really necessary. And what we're going to see in just a second is the Laplace transforms of these things, which is really what we're building toward, so that we can take the Laplace transform of something like this by breaking it down into pulse functions and unit step functions, and then if we can take the Laplace transform of each one, then we can take the Laplace transform of the entire piecewise continuous function. So let me show you those Laplace transforms. And these are, again, included on your Laplace transform sheet. And I won't prove any of these. They're mostly just formulas to apply. The first one, the unit step function, is, of course, the simplest. It is e to the negative as over s, where a is the point at which the step function turns on. And then for the others, if you have a function times a unit step function, so that would be like this last one where we have t squared over 10 times u of t minus 8, that you would take the Laplace transform of the original function, and then you would multiply by e to the negative as. And then if you don't have it shifted, so if this one's not shifted, then you can think about if you need to adjust for that. So this one needs to be adjusted by essentially shifting from t minus a to t, so adding a to it. And so that's the Laplace transform of f of t plus a. So we'll see an example in a second to see how that works. But if the value inside these two functions doesn't match, if we just have t and t minus a, then for the Laplace transform of f, you have to adjust it so that it kind of fits this more closely. And then lastly, the Laplace transform of the pulse function. If we know the Laplace transform of the individual unit step functions, we can do those individually and subtract. And so ultimately the resulting Laplace transform of the pulse function is what we see there at the end. So as long as you know that, you can find the Laplace transform of the pulse function.